All right, I'm going to start off with another actually simple case of a wire and a magnetic field. But in this case, I wanted to give you some magnitudes of some of the things you might expect in everyday life. So, like what kind of force would be acting on on a wire that you see crossing a large field out in the country? Uh, or also, what about a wire carrying much smaller amperage in an MRI device? Basically, the MRI machine that you use in the medical that's used in the medical field. So we're going to just do the F equals, or the dF equals I dL cross B. Of course, this is a simple case, so the integrals all disappear. I'll just sort of highlight how that happens. But let's get started with the document cam. So here's the problem that we're actually considering. We have basically a magnetic field of a typical earthly magnetic field. It ranges anywhere from 0.3 to 0.65, 0.7 Gauss. And a Gauss is 1/10,000th of a Tesla. And Tesla's the unit that we use in the SI system. But in this case, we've got it pointing into the paper. And then, of course, we've got a wire whose length is 1 meter and it's carrying 200 amps. Now, how did I come up with that 200 amps? Well, it's not uncommon for a wire that you might see going across the country field, that are the ones that are really high on the tall towers. It's not uncommon for those wires to be carrying enough electricity for, say, 10,000 homes. If that's the case, every home gets about 200 amp service. So 200 times 10,000 gives you about 2 million amps. But because they don't want to waste so much money on I squared R heating, that is, you know, power equals current times voltage, or if you take into account the fact that you really can't control how much the voltage is going to drop, because it's basically just a function of how far the wire has to run. So you can end up getting I squared R by replacing the V with IR. So the power equation, instead of being P equals IV, becomes P equals I squared R. And what you see is the larger current, the larger the power loss. And in this case, doubling the current would actually increase the power loss by a factor of 4. Tripling it would increase it by a factor of 9, so on and so forth. So what's done is they actually step up the voltage from what would normally be on the order of 100 to 200 volts, 120 say. They step that up till the voltage is really high, but that whatever factor you step that up, it's going to be exactly the same factor that you step the current down. So instead of having 2 million amps going across there, you can actually step the voltage from 100 up to 1 million volts, and that's a factor of 10 to the fourth. So the 200 amps times 10,000 would become just or excuse me, the 200 amps times 10,000 would just become, when you divide it by 10,000, just 200 amps total. So it's probably not a horrible guess at how much current might be running through a particular wire over a high field. Obviously, if they're serving more than 10,000 houses, it'd be a bigger voltage, or excuse me, a bigger amperage. And then part B, I'm going to ask you to try to consider, what about the same sort of wire? This time it's going to be only carrying on the order of 4 amps, which is still a significant current, but the magnetic field is going to be really huge. It's going to be like you have in a nuclear magnetic resonance imaging device, the tubes that you slide into that can see soft tissue, and as well as bones and stuff. It's normally they just call it MRI because the N is nuclear, and that kind of scares people, so they just leave the N off. So let's work these problems. We do know, for instance, that our equation for the force is dF is equal to I dL cross B. In this case, you could sort of say, let's draw a coordinate system like X, Y, and then of course, right-handed coordinate system would force the Z-axis to come out of the board. So I'll put a Z-axis like that with just a dot there. So Z sticks out of the board. If that's the case and we have a uniform magnetic field, then the magnetic field B would just be 0.6 Gauss in the negative K hat direction. So that would be the actual magnetic field. The DL in this case could just be, let's say, dx, and of course the I hat direction. And of course, we're going to integrate it from L equals, or excuse me, from X equals 0 to L, which is just 1 meter. But you see everything's a constant, so really the integral is just going to become dl becoming basically a length L. So we end up getting F equals I times L crossed with B. Of course, you have to take into account how's the DL oriented with respect to B, and we know that for a vector A cross B, the magnitude of that vector is the magnitude of A times the magnitude of B times the sine of the angle between them when they're tail to tail. So that would be your angle theta. Okay, so in this case, our vector B is pointing into the page, and our vector DL is pointing this way. So you can see that the theta is actually equal to 90 degrees. So we get I times L times B times the sine of 90 degrees, which sine of 90 is just 1. So F, at least in magnitude, is just going to be BIL. Okay. Now, as far as the direction goes, the way it works is DL is pointing this way. I can move my hand anywhere I want so that my pinky is always parallel to the wire, actually parallel pointing towards the direction the current is going. But I need my hand to be in such a way that my palm can point in the same direction as B, so that ends up being that. And when my hand's in that position, obviously what I see is the force is pointing upward. So it's in the Y direction. So I could make this a vector by saying J hat, putting a vector symbol over it and putting a J hat. Now that's kind of neat, because if we're looking at this side on, which is really the plan, then this actually counteracts the weight of the actual wire. You'll see the force isn't that huge though, but still it's kind of neat that you can do that. So for part A, we have F is equal to BIL J hat, which equals, in this case, 0.6 Gauss is actually 60 microtesla. I is 200 amps, and L is 1 meter. And we have a J hat there. Of course, 60 microtesla is in fact 60 times 10 to the negative 6 Tesla times 200 amps times 1.00 meters, again with the J hat, which equals 200. I can basically make that a factor of 10 to the 2. That'll make this 10 to the negative 4. And then there's another factor here that'll make it 10 to the negative 3. So I get 6 times 2 is 12 times 1 is 12 times 10 to the negative 3. And the units work out that a Tesla times a meter times an amp is in fact a Newton. And from that, you can, of course, try to make this more like scientific notation. It would be 0.012 newtons in the J hat direction. And checking that with our calculator just to make sure, because I sometimes screw it really royally on my multiplication when I do it in my head. $60 times 10 to the negative 6 times 200 times 1 gives me 0.012. So I got that right. Now, again, that's 200 amps going through a really weak magnetic field, but still a pretty big amperage. Let's look at the same length of wire, but this time going through an MRI device and only carrying 4 amps. In this case, we're still going to get F equals BIL J hat, only this time our magnetic field is 4.0 Tesla. That's upper end of the typical range of an MRI device. I think recently I heard they might get as high as 10, but I'm not certain of that. A current of, let's say, 4.0 amps. And then again, a length of 1 meter. So obviously you can tell here we end up getting 16.0 newtons in the J-hat direction again for this guy. So with an MRI device, it probably wouldn't be unheard of to get a force of 16 newtons on a wire if it happens to be carrying, a whole 4 amps, which again is a huge amount of amperage, especially for something inside of an electronic device. But it's pretty typical for what if you're talking about coffee pots and things like that. 4 amps is not unreasonable. I don't know the electronic machinery necessarily that's in a MRI device, but certainly that 16 newtons is appreciable. Remember, a newton is about a quarter of a pound, so this would be a force of about 4 pounds. So that basically works those two problems. Hope that's somewhat helpful. One of the figures I use, by the way, is that this is for conversion. 1 Gauss is equal to 10 to the negative 4th Tesla. Or 10,000 Gauss equals 1 Tesla is another thing. Well, I hope that helps. Have a good day.